Hello. Audio test. I think we live. Hello everyone. Welcome to the OneClass channel. My name is Millan, and I am a software engineering student at Carleton University in Ottawa, Canada. Today, we will be going over some commonly asked physics questions at both the high school and university or college level. If you're interested in getting help with your homework, or if you're interested in tutoring, check out the links in the description below. Sounds good. Today is a beautiful day for physics. Well, every day is a beautiful day for physics, but today is also one of those days. Just gotta switch over my screen super ASAP fast. And we can get our party started. Get this physics party started. Cool. So let's start the stream here. And let's get it moving on our first question of the day. So our first question of the day is asking us, in circular motion, a tangential acceleration can change the magnitude of the velocity, but not the direction. Explain why, or explain your answer, but let's just interpret that as like explain what is going on. Why is that even possible? Okay, so suppose we have some circular type motion looking like this. Okay, and maybe we got like, someone like this. Oh, let's get back to a brush. We got like a little car here. And, it's kind of like we're driving in a roundabout, driving in the circular path. So, in circular motion, there are two types of acceleration. There's the acceleration inwards, AC, centripetal acceleration, centripetal, centri, and then petal, like a flower petal, acceleration. And that centripetal acceleration is not the tangential acceleration that we're looking for, but this is why something moving in a circular path is going to continue moving in a circular path, because it requires that you accelerate, like you change your velocity slightly to follow the curvature of the path. So that's what is caused by the centripetal acceleration. It's the centripetal acceleration is what's causing the curvature in the travel path of the item. In this case, it's like a car driving in a roundabout. Maybe that could be our example to visualize. But otherwise, it could be like it could be an electron going in a circular path inside an electric field. It could be you're on a merry-go-round and that's what you're feeling. Okay, so centripetal acceleration is what goes towards the center and what causes your it's what causes your direction to change, what causes the curvature in your path. Now the other acceleration, serious, so we're good again. Cool. So the tangential acceleration is what is like tangential acceleration. This is controlling how fast you are moving around the circle. So if we're in the car driving in a roundabout situation, tangential acceleration is pretty much like how much you're putting the gas pedal down or how much you're putting on the brake pedal. If you have a negative tangential acceleration, this would be like what you would see on your speedometer, and changing this or this will causes change in velocity around the circle. On the centripetal acceleration, this defines the radius of the circular path. Circular path. Okay, so keep in mind AC, centripetal, and its cousin, AT, tangential acceleration, they are always perpendicular, 90 degrees separated from each other. Okay, and AC is always towards the center of the circular path, and AT, well, that kind of depends on the situation. Like if you're accelerating, increasing the speed, like in a roundabout, hitting the gas pedal, it would be in the direction of travel. But if you're pushing the brakes, it would be in the opposite direction as the direction of travel. And the reason, and it doesn't change the direction of the velocity, because it's going in the same direction, or it's along the same line as the velocity. Even if it's negative and it's going the opposite direction, if I'm moving forward and the AT is going backwards, they act upon the same line. So the acceleration does not cause any, the tangential acceleration, that is, does not cause any change in the direction of the circular moving object. It is only AC, centripetal acceleration, that controls the direction, because it is acting in a non-collinear, meaning it is not on the same line as the velocity, so it's going to change the velocity's direction. So, yeah. Awesome, yeah, it's pretty much the exact same explanation. So, the above solution is good. Good job. Nice. Fun times with physics. Physics to the limits. I love physics. It's a great time. Anyways, the next question that we got on the menu today is, for which of the following vectors, we got three options here, is the magnitude of the vector equal to one of the components of the vector? Okay, so first let's talk about how do we find the magnitude of a vector. Most of the time, like if you have a vector, it's typically going to be something like a V with an arrow on top. I like to draw them as like half arrows because they're easy to draw, but sometimes you might have full arrows. Sometimes you might have them in bold, but bold is tough when you're not on a computer and you can just do bold. So typically you want to just do it with an arrow on top. I prefer, this is my preference. So if you want to show the magnitude of a vector, show with absolute value of a vector. Absolute value, like when a vector is inside, it means a magnitude. But sometimes, because sometimes people get confused with that, it can also be with the double absolute value. And that's just to show, like, don't get this confused with absolute value. We're taking magnitude. But it's kind of like the same thing. Now, the formula to calculate this, those two are equal, it is the square root of the sum of all components squared. So it really does have like a similar type of vibe to Pythagoras' theorem. So very reminiscent. Of Pythagoras. Pythagoras was a pretty smart guy a long time ago in Greece, I believe. Yeah, pretty smart guy. Knew a lot about triangles. Anyways, let's take a look at our options here. And then we can, using our options, we could calculate their magnitudes. And then it's asking us which has a vector that is, which magnitude is equal to one of the components. And then we can tell. Now, the magnitude is always bigger. Is always bigger or equal to any individual component. Okay? Magnitude is always bigger or equal. And the only time that it's equal is when we only have one direction. And we have, it seems, B and C are both like that, but we'll get there when we get there. So let's start off with A. The vector A is equal to 2 in the I direction, 2I. I'd like to draw my eyes like for the unit vector with like a triangle hat on top, or pour vous qui sont français, un accent circonflexe. It's just easier to draw. And then we have 5 in the J direction. Okay, so if we wanted to draw this like on a grid, like 1, 2, 3, 4, 5, 1, 2, it would go 2 in the I direction, and this is X, and this is Y, and this will be 5 in the Y direction. It would be here. So that would be A. Okay, and you can kind of see this definitely has some Pythagoras theorem type of energy. So if we wanted to find the magnitude of A, pretty much just the length of that arrow A, we would want to do, well, in this situation, it should be fairly obvious that we have a right angle triangle. Its height is 5. Its, I guess, side length is 2. So the hypotenuse, we know that it's got to be, well, let's write it out properly. The magnitude of A is equal to the square root of the sum of 5 squared plus 2 squared. The order that you do them doesn't really matter, because in the end it's all going to work out. So we have, well, 5 squared, 5 times 5, 25, 4 squared, 2 squared, 2 times 2, that's 4. So it's going to be the square root of 29. Is equal to the square root of 29, and I think that is going to be a very decimalicious number. Send it to my calculator to find out for a fact. If we got the square root of 29, we get 5.3851, on and on and on and on. Very big decimalicious number. We don't really need to worry about those decimals, and we just know that this is our magnitude, about 5.3851. Okay, awesome. Now, here's the thing. The question is asking, is the magnitude of the vector equal to one of the components? Well, is one of the components 5.3851? I don't think so. All of those components are smaller than the magnitude, which is pretty true. That is a good key that, well, this rule is certainly applying. Magnitude has to be bigger than or equal to any individual component, and it is. Okay, so because of that, because the magnitude 5.3851 on and on does not match with any of the components, we can disqualify A. A, not okay. I know we like to say it's A okay, but in this case, A, not okay. Cool. So now we can try option B. So we know option B is equal to, well, here they have it written as negative 3j, but another way that we can write this is 0i minus 3j. They're actually equivalent. It's just sometimes we don't write the zero terms because, it takes effort to actually move your hand and your pencil and write that around. So we just want to write, like, if there's only one component, it's going to be like that. Now, I can tell you pretty confidently that I know the magnitude of this is going to be 3, but if we want to be more proper and use the magnitude equation, B is equal to the square root of the component squared. So we got 0 squared plus negative 3 squared. That's just going to give us 3. Well, because 0 plus 9, negative 3 squared, that's 9, positive 9. So the squaring neutralizes the negative. Plus 0 is 9, the square root of 9, plus minus 3, but let's just worry about the plus for now. So it's 3. Now, is 3 the same as its component, as any component inside B? Technically, yes, but I think with option C, we see that we have a positive single value. So I feel like C is going to be more right than B, because you could argue that signs don't agree. But that could be controversial because you could say, well, the magnitude is equal to one of the components, because I guess the magnitude explicitly written out like this, like it would be plus minus 3, and it would be valid to say, but it would be more correct. Sometimes you have to choose the most correct solution, even if there are multiple controversially correct solutions. But I know for C, we're definitely going to come to a non-controversial conclusion. Okay, so let's actually see how that works. So C is equal to plus 5 in the k direction. The k direction corresponds to the z direction on your xyz axis type plane. So we could rewrite this if we wanted to be more formally proper. 0i plus 0j, because we have no contributions in the I or j direction. Okay, and then we add 5k. Okay, and if we want to do the magnitude of this, even though there's 3 dimensionals, or there's 3 components, meaning we're in a 3-dimensional situation, we still want to use the same like Pythagoras type of magnitude calculation. Now this magnitude calculation works whether it's 2-dimensional, 3-dimensional, a billion dimensional, whatever dimension you want. This is always the same procedure that you find your magnitude with. Yeah. Oops, that's not B. To be or not to be. Not to be in this case. It's C. You see what I mean? Okay, so here to write it out formally, we got 0 squared plus 0 squared once again, plus 5 squared, and it should be fairly straightforward to see that these neutralize each other. They zero themselves out, and that's just going to be the square root of 25, and that's 5. Now, do those match? Match? Yes. And we're going to choose option C because this will be uncontroversially correct. Option B could be like controversially correct, but you know, in multiple choice situations where you only really want to pick one, choose whoever feels more correct. In this case, C feels more correct because you don't have to argue to say like, oh, a negative magnitude would be valid as well. Okay, so yeah, we would come to the conclusion that C is the one that satisfies the condition that the magnitude is equal to one of the components, and yeah, the junior tutor here wrote in the same answer. We got C, so the above solution is good. It's good. Awesome. Ain't this a fun time? I'm having so much fun. Okay, the next question that we got on the menu today, a little bit of a spicier question, is we got a 150 kilogram merry-go-round in the shape of a uniform solid disc. It's got a radius of 1.5 meters, and it is set in motion by wrapping a rope around the rim and pulling on the rope. And the question is asking, what type of constant force must be exerted on the rope to bring the merry-go-round from rest to an angular speed of 0.5 revolutions per second in 2 seconds. So we're applying the force for 2 seconds. So typically for questions like this, it would feel better with a diagram, but we don't have a diagram here, so we can improvise our own. So here I have like a jar of like protein powder, and we can kind of simulate our merry-go-round with like this. It kind of looks like a hockey puck. Here in Canada, hockey's pretty popular. So, you know, as this thing, it's going to start from rest. Oh, it's going to be kind of tough to balance. And then imagine we have a rope around it, and then we let it rip, kind of like a Beyblade. Pretty much exactly like a Beyblade. Yeah. Or like some tops or dreidels are spun with strings as well. Yeah, so that's pretty much what happens if we took some tape, wrap tape around here, and the tape is not very sticky, and we pulled on it real fast, we would see and we would expect this to start spinning. Oh man, I just threw that across my room. It's okay, I'll get that at the end of the stream. Okay. Nice. So that's kind of like a model of what's going on. Let's draw a diagram for ourselves to kind of make sense or make visual sense of what would be going on in this situation. So suppose this is our merry-go-round, and it mentions that our radius looks about center. our radius is 1.5 meters. 1.50 meters. So 3 sig figs. Significant figures are significant, believe it or not. The mass, let's call that M, is equal to 150 kilograms. It's pretty heavy. Heavier than me. But that's kind of expected because, you know, merry-go-round. It's pretty heavy. And I guess we're going to ignore the mass of the rope because that kind of would change things. But it doesn't mention it, so I'm going to assume that we're allowed to ignore it. And our initial speed, our initial angular speed, let's call that omega I. Omega represents angular velocity. It looks like a W. It's not a W. It's the Greek letter omega. Now, why don't we call it W? Reasons. Yeah, exactly. It's omega. So its initial is angular speed. Well, it starts from rest. So right here it says it starts from rest. So initially 0 radians per second. And our final angular velocity, they said it's 0.5 revolutions per second. Now we want to have that in radians per second, and we know that 1 revolution, 2 pi radians, so it's going to be 2 pi times 0.5 radians per second. So 2 pi multiplied by 0.5 rad per second. And if you look closely, the 0.5 and the 2, well, they neutralize each other to just be 1, so we just have pi radians per second. Okay, now another important detail that they mentioned to us is that the merry-go-round is in the shape of a uniform, solid, horizontal disk. Okay, now the reason why they mentioned that and the reason why that's significant is because we need the moment of inertia to know how this disk or this merry-go-round is going to interact with the force that is applied on it. Now, what is the moment of inertia? Moment of inertia. A moment of inertia is pretty much how difficult it is to spin something. Yeah, so let's think about some examples. Like something that is very, very large and heavy is going to have a much higher moments of inertia because, well, it's going to take some effort to actually get it moving and to get it start spinning. Or, okay, imagine this. So you ever seen like big car tires? Like you can't really slap them and expect them to like start really spinning. But for a much smaller wheel, like maybe like a skateboard wheel that could be like the size of maybe a fruit or something, you could slap that and you'll see it really start spinning. And you're not going to be able to do that with like a car tire because one, the car tire has a significantly larger moment of inertia, so that same force of the slap is going to cause less of a rotation. Okay, so the thing about moments of inertia is that they are dependent not only on mass, but they're also dependent on the shape of the object. Now, in this question, we don't necessarily want to show that we how to calculate the moments of inertia because that in itself is quite a process. But we know from common shapes like disks that the moments of inertia of a disk is just inertia is gonna be 1/2 the mass times the radius squared. Okay, that's the moment of inertia. For now, just treat it like a property of the spinning disk. But maybe in the future, you might see some situations where you have to calculate the moment of inertia. It's not necessarily hard. It's just a very long and delicate process. Okay, but this is our moment of inertia for a disk spinning like a, spinning without like flopping. Rolling, I suppose, is the direction of the spin. Okay, so if we wanted to calculate this, well, we know that we have 1/2 the mass, 150 kilogram, And the radius, that is 1.5 meter, 1.50 meter. We got to square that whole thing. So we got, pull out the handy dandy calculator to help tell us what is going on here. 1/2 multiplied by 150 multiplied by 1.5 multiplied by 1.5, because that is squared. Fair and square. And the moments of inertia that we got is 168.75 kilogram meter squared. Okay, it's fairly important to make sure that your units are in line, because losing a unit throughout your calculation could be quite uncomfortable to deal with. Okay, now we know the moments of inertia, we know its initial and final angular velocities, and now we just got to find out what type of force would cause your angular velocity to change from 0 up to pi radians per second, assuming with the current moments of inertia. Okay, so this is kind of a diagram here of how they're showing off, like kind of how that Beyblade merry-go-round is going to rip. And we know that we want to use the torque equation. Okay, so the torque is like a force applied over a it's kind of like how force causes things to move in a straight line. Torque causes things to rotate. So if I have like a steering wheel, I apply a force to it to make it turn, but it's actually causing a torque because it's gonna spin. So torque is like force, but in a spinning kind of sense. It's how much you want to make something spin. Okay, so torque is represented with the Greek letter tau, torque, which is equal to the force times the radius, and a higher force will cause, of course, more torque, and a higher radius is going to cause more torque. Like you can even look at this with a door. Is it easier to open a door when you have a large radius, like when you're farther away from the axis of rotation, or when you're closer? It's obviously going to be easier when you're farther away, so higher R, higher torque. And we could also write this as the moments of inertia, I, multiplied by the angular acceleration. So here, that is angular acceleration. Okay, now we're trying to isolate for R. We're trying to isolate for the force. So we can divide both sides by R. Force equals I multiplied by A. Whoop, not A, alpha. They are not the same, even though they have some visual similarity. Divide by R. Now, how to find our angular acceleration? Well, acceleration is the change in motion with respect to time. Angular acceleration is the change in angular velocity with respect to time. So it is really just the final minus the initial divided by the time. And the time here was 2 seconds. Okay, so initially for the angular acceleration, what we're going to have is alpha equals omega final minus omega initial divided by time. And we have values for all of that. So omega final is pi rad per second minus 0, because it starts at rest. The question mentioned that, so that's good. Minus 0, and divided by t is 2 seconds. Okay, so alpha is really just pi over 2 radians per second, or we could also write that as per second squared. Okay, so we have all the values that we need, and we can just plug this into the equation and come out with the value for R. So yeah, cool, let's do that. So for I, the moments of inertia, let's write that. Moments of inertia, we had 168.75. 168.75 kilogram per meter squared. Not per meter squared, kilogram meter squared. Alpha, we have radians. Oh, wait, 2 pi. No, not 2 pi. Pi over 2 rad. That's pretty rad, bro. Rad per second squared. That whole thing divided by the radius, which in this case is radius is 1.5 meters. 1.50 meters. Okay, let's ask our handy dandy calculator, what is the numerical result of this calculation? Okay, so 168.75 multiplied by pi, divide by 2, and divide by 1.5. And the result of this is 176.71. Numbers are a little bit different than the one given by the result, but it's not a significant. It's not by a significant amount. And let's and that's not really a big deal, but let's take a look at the units and see how they cancel out. So the meters down here will neutralize one of the meters, so it's not going to be squared anymore. It's just going to be kilogram meters. And then radiant, another way you could say radian is meter per meter. Radians is not like a real unit. It's kind of spicy that way. Yeah, radians isn't a real unit. So it's really just 1 divided by second squared. So in the end, we get a kilogram times meter multiplied by meter, divide by second squared. And you can see, if you look closely, meters per second squared, that's an acceleration. Acceleration times a mass, that would make a Newton. So, 176 newtons, or 177. Let's not forget about our significant digits. So if we go back to our question, we got 3 significant digits, so our final answer should be 177 newtons. Okay, and that's pretty much right here. Yeah, and it would round to the same result. So yeah, the above solution is good. Solution is good. Awesome. Ain't this a fun time? I think it's a fun time. Cool. Okay. Next question that we got on the menu today is, how are the units of volts and electron volts related to each other? How are they different from each other? Okay, so we have volts versus electron volts. Okay, how are they related? Well, they are related in the sense that they both, forgot the T. Whoops, that's kind of a... My spelling normally is good, but sometimes I surprise myself. Anyways, how are volts and electron volts related? Well, let's just talk about what they are as individuals before we talk about how do we compare one to another. So volts is a unit of electric potential. And this electron volts is a unit of energy. One volt is equal to 1 joule per coulomb. Okay, so you can kind of see how they relate to each other, because the definition of a volt is 1 joule divided by coulomb. Like it's the amount of energy that a single coulomb of charge would feel at that particular point, the amount of potential energy. Now an electron volt is, well, really, you multiply the definition of a volt, you multiply that by the charge of an electron. That's going to neutralize the coulomb down here, and that's going to give you electron volts. And you see how only joule is left. Joule is a unit of energy, so you would only have a unit of energy left for the electron volt. Now the charge of a let's actually do that calculation. So 1 electron volt, electron volts are written as lowercase e uppercase v, is equal to 1 volt multiplied by the charge of an electron. So 1 volt, let's rewrite that instead as joule per coulomb multiplied by the charge of an electron, which we know is 1.6 times 10 to the negative 19 coulombs. And, well, you see how the coulomb down here and up there neutralize each other, and we'd only have joules and this number left. So 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Now, is that a number that you should memorize? Not necessarily, but if you use it a lot, it'll be hard not to memorize it. So, I've seen this number a lot, so it's deep inside my noggin. Okay, so they differ in terms of the property that they represent. So electric potential for volts, energy for electron volts. They're related in terms of how you can use one to calculate the other. So you could also get a volt given an electron volt. If you just divide out the charge of an electron, well, you'll get a volt. It's really that simple. And yeah, it's a unit of energy, or unit of energy versus unit of electric potential. Yeah. And volts are typically used more in like electric circuits. Electron volts are used in like nuclear physics a lot. So it also depends on what type of things that you're doing. That will kind of also increase or decrease the likelihood that you will see some of these units. Like electrical engineers will see volts on the regular. Nuclear physicists, they'll see electron volts on the regular. So yeah, the above solution is good. Or if you're just a really sharp person, you'll probably see both of them a lot. Cool stuff. Okay. So the next question that we got today, Eli, the Iceman. It might sound quite scary, but it really is not that scary. Eli, the Iceman, might sound like a supervillain. He's really a nice guy that can tell us some nice things, okay? So Eli, the Iceman, the real info that we want to extract from here is E, L, I for Eli, and ice. The E's represent electromotive force. Electromotive force, aka the voltage. And the I represents current. L represents inductor. The reason why L is used for inductor instead of something like I is, well, I is already used for current, and it would be too confusing to have, current doesn't even have the letter I in it. Why do we use the letter I for current? Because someone way back a long time ago said so, and everyone just learned from them, and they said, I'm too lazy to change it. It's kind of backwards, but it's the way it is. L is just the most similar looking letter to I, so that's why we use L for inductor, even though inductor doesn't have a single L inside of it. It is what it is. And C represents capacitors. Okay, Now we kind of decoded what we mean by Eli and ice, um, and we'll get to civil later. But the reason why this is useful is in electric circuits, especially AC circuits, because AC circuits is when these inductors and capacitors, also known like together, you can refer to them as storage elements. Only in AC circuits are they really gonna be used. Otherwise, they're kind of just like inductors are just wires in DC, and capacitors are just like disconnected from the circuit in DC. So if we have an inductor L, we have plus minus, we have VL, the voltage of L, and we have the current, IL. And then we will have, in a capacitor situation, capacitors look like this, like kind of like sandwiches. I like sandwiches. Plus minus, we'll have VC, the voltage of the capacitor, and the currents going through the capacitor, IC. Keep in mind, the current in a capacitor doesn't exist when it's DC. This is AC only. Okay, so in the case of an inductor, AC signals are mostly sinusoidal. Meaning like this. But sometimes they don't line up with each other. Actually, very rarely do they line up with each other. So maybe in this example, we could have I as the red line and V as the black line. Now, what we really want to extract from here, from the Eli, is that when it's an inductor, E is before I in terms of phase. So in this case, you see how the voltage corresponding to E is kind of ahead of I. I just seems like a delayed version of V. That means that it has to be an inductor. So inductors have voltage leading over current. But if I wanted to do another example where current leads, like that, for IC, let's call it IL, and VL, and then current leads VC. In capacitors, current leads voltage. In inductors, voltage leads current. Okay, so this is kind of just saying like which signal is more forward in the phase, and yeah, depending on the specific storage element, it will either be the voltage, the EMF, or it will be the I, the current. And another way that you can remember this is with the word civil. I know a couple people who are in civil engineering. They're pretty cool. And it is largely working the same way. So this part of the word civil, VIL, is for inductors. V leads spelling. V leads I. And for here, in capacitors, let's make them blue. I feel like capacitors kind of got some blueness in them. Capacitors. I leads V. These are all different methods of kind of remembering the same thing. It's just who leads who when you have an AC signal, because the current and the voltage will almost always be out of phase. And with Eli the Iceman, or just the word civil, you can hopefully easily keep track of who leads who depending on the storage element. Yeah, and the amount that they lead by is 90 degrees. So it's kind of like you would just have like a plus 90 degrees in that in the term of the sinusoid. Maybe something like this, like sine. Whoops, I'll write it down here so it's a little bit more clear. You might have something like sine omega t plus 90 degrees for the leader. Okay, so yeah, that pretty much covers this question. So yeah, the above solution is good. Is good. Cool. Awesome. Exciting stuff. Okay, cool. Let's keep it moving to the next question on the menu today. Oh, this is so much fun. Okay, the next question that we got today is how do we convert radians per second to meters per second? Now, this question is a little bit vague, so we got to do some, of our own inferences to kind of make meaning of this question because, a one-sentence question typically gets a one-sentence answer. So let's expand on this question. Let's assume that the radians per second is it's your angular. Well, of course, that has to be your angular velocity, but let's say it wants to get the meters per second, your tangential velocity, given your angular velocity. So let's kind of draw out a circle to talk about what in the world is going on here. So suppose we have the circle of radius, let's call that r. R for radius, makes sense to me. And we have a little dude driving a car in a circular motion. This could be you in a roundabout. And if you're driving in a roundabout, you look at your speedometer. Okay, I'm driving 10 kilometers per hour inside this roundabout. How your radians per second is kind of saying what's the change in your angular position. So I'll draw this out in a different color. So this will be theta. And angular velocity omega is equal to the derivative with respect to time of theta. Okay, so you take the derivative with respect to time of the angle, and that will give you the angular velocity. So the rate at which you're increasing that angle is your angular velocity. If you're going faster, more angular velocity because you're doing more circle per second. So that's how they're related. Like if you're driving in a roundabout, if you increase your speed, your angular velocity is going up because, well, the time it takes for you to go one whole way around that circle is less. Okay, and how they are related is that v is equal to radius times omega. So this will be linear velocity. This will be angular velocity. Angular velocity. And that will be radius of circular path. Circular path. Okay, awesome. So that's pretty much how you can relate one to the other. And it kind of makes sense. Like, let's say if radius is really small, you would expect or let's say you have a constant angular velocity. At a small radius, you'll have a small linear velocity because, you're going one loop per second. If the loop has a circumference of 1 kilometer, that's a small linear velocity. If the loop, if you're doing one loop per second and the radius of the loop is the Earth, and, the circumference is, the circumference of the Earth, well, your linear velocity is going to be quite quick if you have one circle or one complete radian per second, or 2 pi radians per second. So yeah, this is how you relate them. And let's say, well, this is like v equals r omega, but you can also just divide both sides by r. So omega, not w, equals v over r. Omega is not a w. Thank the Greek alphabet for that. Okay, and this is how you, if you know one, or if you know 2 of the 3 terms in this relationship, you could find the 3rd term, and then you could give yourself a high five because you have mastered the conversion sequence between angular and linear velocity in circular paths. Remember, it has to be circular paths. If that's an oval, well, it ain't that simple. If this is an irregular shape, this will not work. But if it's perfectly circular, or if you approximate it to a circle, this will be a good strategy to proceed with. Okay, so the above solution is good. Very good. Yeah, v equals r omega. Okay. Let's keep it moving, and we can move on to our next question on the menu today, which is 3 words, magnitude of displacement. Now, we're going to need to make some assumptions about what this question is really asking for, because 3-word questions typically lead to 3-word answers. So we want more detailed questions. That'd be helpful. But we can work with what we got here, magnitude of displacement. Let's first talk about what displacement is in the first place. Displacement. This is definitely a vector. So we can draw it like that. Vector. Unlike distance, which is scalar, displacement represents the shortest possible distance between 2 points of interest. Shortest distance between 2 points of interest. Okay, and typically, a lot of the times this will be in 2 dimensions, where we can use like Pythagoras theorem, but in 3 dimensions we can have like our 3-dimensional Pythagoras, and it will also work out as well. Okay, so given the diagram that our junior tutor here has written out, we have point A down here somewhere and point B, and we have some XY plots, or we're on an XY grid, 2 dimensions, and they're going to have different values. Let's actually upgrade the intensity of this question, and we can move it into 3 dimensions, because, well, most of us live in 3 dimensions, and it would be helpful to, do math in 3 dimensions. So we can do a 3-dimension, 3D example. If we get 3 Ds, hopefully we won't see any Ds on our report cards, because, the more intensity you do things, it's like, sometimes if you're doing athletics, you want to train with ankle weights on so that you feel extra strong when it's competition time. Same type of thing. If you increase the intensity when you're doing your practice, when you're doing your homework, when you're doing your training, the test will be lightweight if you have higher intensity training. So yeah, let's do a 3D example. Suppose we have 2 points, 2 given points, and we're gonna have let's say we have point A, and point A has points like -1, 0, +1, and we have point B, which is 5, 7, 2. Just completely random numbers that I'm just synthesizing out of my noggin, and we're trying to find like the displacement vector between them and the magnitude of them. So between points of interest, we want to get our displacement vector, and then once we have our displacement vector, we can get our displacement magnitude, or magnitude of displacement as they write it here. Okay, so we want to make distance vector. And let's call that r. We use r because it's kind of like a radius, a radial distance, kind of like radial distance, because it has to be the shortest path away. So that's the reason why we're doing that. Okay, cool. So really, the radial distance is going to be like a, or let's say we're going from A to B. Now, it would be different if we went from B to A, but now that I mentioned that we're going B to A, what we want to have here in our equation is going to be a little something that looks like this. So it's going to be bx minus ax, that's in the I direction, plus by component minus the ay component, put that in the j direction, and plus, well, it's going to follow the same pattern, bz minus az in the k direction. Okay, now it's always going to be destination component minus start point component. So you see on the vector we specify AB, the vector from point A to point B. Well, A is going to be the start, so A is always subtracted. B is the destination. B is always the non-subtracted, the receiver of the subtraction, if that kind of floats your boat. So let's sub in our numbers and let's see what goes on here. Bx is 5. 5 minus 1 in the I direction, plus what's in the j direction, 7 minus 0. Well, that's nice and easy for the math. And in the z direction, we got 2 minus 1 in the k direction. Okay, and then RAB. Let's simplify this. 5 minus 1, 6. 6i plus 7 minus 0. That's a nice easy one. 7j plus k. Just k. Well, I mean, it does have a coefficient of 1 in front of it, but we don't need to write the 1. We know it's there. So this would be our vector. And now we want to get the magnitude. Magnitude of displacement vector. We're going to do it like this. RAB. Sometimes people write it in absolute value. That's to represent magnitude. It is also occasionally written as double absolute value, RAB. And that's just to avoid the confusion of absolute value. But generally, if you see this a vector inside, you know it's a magnitude. And then we're going to do a very Pythagoras type thing. Even though it's three-dimensional, it will still work out. So in this case, it's going to be the x component. In this case, it's going to be 6 squared plus 7 squared plus 1 squared. And pulling out the calculator for that, 36 plus 49 plus 49 plus 1. That's equal to the square root of 86. Is equal to RAB. Which in this case, R to the power of 0.5, which is the same as square root, 9.27. On and on and on. Because that's a big, long, decimalicious number. So we can just write it like that. But as a general rule is general rule for displacement vectors. Displacement vector magnitudes. Actually, not just displacement, just all vector magnitudes. General rule for all vector magnitudes. It could be force, it could be displacement, it could be torque. It looks like this. So is equal to the square root of the sum of all components but make sure you square the components before you add them up. Okay, so as a general rule, that's the equation that you want to use for getting the magnitude of a vector. Any vector, force, displacement, torque, electric field, all those vectors, you can get their magnitude this way. Okay, so yes, so the above solution is good. However, above solution is good, however, could be improved by using a general magnitude equation that can work in higher dimensions, 3D situations. Awesome. That was fun. Magnitudes, displacements. Next question that we got on the menu today is, can acceleration be negative? Short answer, absolutely yes. A long answer is the unfortunate reality is that the language that we use in physics needs to be much more precise than the language that we use in regular casual English. So in regular casual English, acceleration is typically associated with increasing your speed. And increasing your speed, like there are many factors in our world that kind of create that association of acceleration always being increasing. But the more physics definition is acceleration is change in speed. Now I could change my speed so that I'm faster, or if I'm already real fast, super fast, I can change my speed to be slower if I just stop. So anytime you change your speed, there is an acceleration going on. Now, so based on that, like if we're driving in a straight line, if I accelerate while we're going faster, forward, quicker, if I have a negative acceleration, like I could be if I'm driving in a straight line and I hit the brakes, I have a negative acceleration. My speed is changing, I'm slowing down, but I'm changing to be faster in the opposite direction. So in that way, you can kind of see acceleration as you're increasing your speed, but you're increasing your speed in the opposite direction that you're going, which results in a lesser overall perceived speed. Okay, and acceleration, the signs of acceleration determine which direction the speed is changing in. Okay, now that was for like a one-dimensional situation of me just driving in a, in a straight line, in a straight road. But there are things move in much more complicated ways than just straight lines. Like think about an airplane flying. Like it has 3 dimensions of movement that it's in. The Earth is spinning itself. Like there's a lot of different accelerations that could be happening in like in various different contexts. Also think about like planets orbiting each other. Like all got like accelerations going on. So depending on the context, the sign of acceleration is going to become less useful. You're going to want to have like the direction specified. So specifying direction of acceleration is often times more useful than just plus minus, especially in higher dimensions. But still keep in mind positive, negative acceleration. You just got to put that together in your mind and got to think about how is the velocity changing. Because, you know, thinking back to our good old friend Isaac Newton, Isaac Newton says that nothing or the speed of something will stay constant unless there is an unbalanced force moving or applied to it. So something that is not moving is not going to move until it accelerates, and the acceleration is caused by a force. And something that is moving very fast is not going to slow down whatsoever until you add a force that will until you apply a force on the speedy object that will change its velocity. Okay, so negative velocity, absolutely don't be afraid of it, but make sure in your mind you kind of keep sense of what direction things are going to be. Okay, so the above solution is correct. Sometimes you can also say a negative acceleration is a deceleration. That could be another vocabulary word that could be useful to describe this situation. Okay, so yeah. Okay, so the next question that we got on the menu today is asking us, how much bigger is the sun than the earth? Now, this question, we kind of need to, the answer to this question depends on how we define bigger. So, bigger, we have two options. Okay, we can do bigger in terms of actual like size, the space that they occupy. Sun is much bigger than us in terms of size, or we can also do mass. Now, mass and size are pretty related to each other, but sometimes we might say that, you know, the mass, like something's bigger than something else because of its mass. We don't always necessarily want to use size. It would be better if the question specified like how much bigger is the sun, or how much bigger is the mass of the sun compared to the mass of the earth, or how much bigger is the size of the sun compared to the size of the earth. Those would be better ways to kind of phrase this question. Yeah, so let's we got our numbers here, which are nice and convenient. So the mass of the sun is 2. So let's do sun. Let's make like a graph here. Sun and earth. And we got mass and size. I guess the one that we have here, just to be nice, we can use radius. Radius. Okay, so we can open up a new tab here. We can do Google mass of sun. Mass of sun, it's pretty heavy. 1.989 times 10 to the positive 30 kilogram. Now what about mass of Earth? Mass of the Earth, pretty heavy as well. 5.972 times 10 to the 24 kilograms. Now keep in mind the times 10 to the 24 is 1 million times smaller than 10 to the 30. So it's at least a million times, or maybe not a million times, like maybe half a million times. Anyways, now let's do radius of Earth. Radius of Earth is 6.371 times 10 to the 6 meters. Just converting like that, k is going to become a 10 to the power of 3, and then I'm going to shift the decimal. That's a comma. And then I'm just going to shift the decimal, and that's going to be another power of 3, or 10 to the power of 3, so that's going to be 10 to the power of 6, and then radius of the sun. The sun is my favorite star, by the way. 6.96 times 1, 2, 3, 4, 5, 6 times 10 to the 9 meters. Okay, so if we wanted to take the ratio, we would just divide the sun by, or the value corresponding to the sun divided by the value corresponding to the Earth, and that would be like how many times bigger the sun is compared to the Earth. Okay, so for the mass, let's do that real fast. 1.989 times 10 to the power 30. That's a very large number. Divide that whole thing by 5.972 times 10 to the power 24. And we'll see that the sun is quite a bit larger than the Earth. It is 33054 times bigger than the sun is that many times bigger than the Earth. So the sun is more than 300,000 times bigger than the Earth in terms of mass. Okay, seems about right. So sun is 300k plus times bigger than the Earth. And let's do a similar calculation for the radius. Now keep in mind those exponents, those orders of magnitudes, is what those like times 10 to the power of whatever is called. So let's do that quick math. 6.96 times 10 to the power of 9. Divide that whole thing by 6.371 times 10 to the power 6. And we'll get that it is about 1,000 times, 1050 times bigger. So the sun is 1050 times bigger than Earth in terms of radius, and here in terms of mass. Okay, so this can just go to show you the importance of precision in the language. So actually, radius of the sun, no, that should be 10 to the 8. So whoops, because it's 600,000 or almost 700,000 kilometers. Be 10 to the 8, my bad. And this would just be 10 times smaller, so it'd be pretty much just like 105. Sometimes we make mistakes, but if we catch them, we can learn from them. Remember, making mistakes doesn't make you dumb. Only repeating mistakes makes you dumb. Okay, so yeah, we can see that we get vastly different answers for how much times the Earth or the Sun is bigger than the Earth, depending on what property we are considering is the defining factor of big. Is it going to be mass or is it going to be radius? So it's a very fascinating solution. The above solution is uses very approximated values for mass, does not do the calculation in terms of mass, does for the diameter comparison, there is no mention of the diameter of the Earth, which makes the answer unclear on where it came from, and would be good to comment on the importance of the precision of language used to ask how something can be seen as bigger than something else. In terms of mass versus physical size. Now, here we just compared radius, but if we compared volume, it would be a whole nother story, because volume is radius cubed, I think, or even cross-sectional area. That could be like another way to describe the size, and we get vastly different answers depending on if we do cross-sectional area, if we do volume, if we do radius, if we do mass. So it's very important that we're very specific with our language, very precise. The precision of the language is incredibly important, especially in STEM. Okay, the next question that we got on the menu today is asking us which of the following materials is the poorest electrical conductor, meaning that electricity absolutely does not want to go down there. Or, I mean, electricity doesn't really have feelings, but electricity would rather go down things that are more conductive. So poor electrical conductivity, it's things that do not transmit electricity well. So an example, wires are designed to be good electrical conductors. So something that would be considered a bad electrical conductor would be something like rubber, because we typically use rubber to stop the flow of electrons. Yeah, so if you ever see like electrical workers, they'll typically have rubber boots, or rubber on the bottom of their boots, not like rubber like rain boots. They'll have rubber on their boots and typically rubber on their gloves as well, because it does not, rubber as a material is one of those materials that is not very good at allowing the motion of electrons. Okay, so we got a couple options here, and they're all metals. Nichrome is a metal, which is a mixture of nickel plus chromium equals nichrome. Basically how that works is they take nickel, they take chromium, they melt them down into like kind of like a metal soup, and when that metal soup of nickel and chromium solidifies again, it becomes a new alloy that's called nichrome. Alloy is another way of saying like a mixture of metals, and the way that they make it, well, they melt them down, mix them up, and then let it solidify. That's how alloys are made. But that's what nichrome is. And nickel and chromium, if we look into our periodic table, these are both transition metals, I believe. And transition metals in general tend to be moderately good conductors. So that does not get disqualified right away. Now, copper is inside wires. Like if you ever cut a wire open, you've seen the copper inside. copper is used because it is an exceptionally good electrical conductor. So which is the poorest electrical conductor? I have a feeling that it's definitely not going to be copper, because copper is pretty good. Aluminum is another, I think it's not a transition metal on the periodic table. I think it would be more considered a metalloid. But, you know, if you're ever in a pinch and you have aluminum foil and you require an electrical circuit, you can improvise wires using aluminum foil. So, and I know sometimes people have done that. I know people in who are in prison and they don't necessarily have access to wires, and they might need wires if they have like electrical projects. I know in prison it doesn't necessarily sound like the greatest place to be doing that, but people have improvised aluminum foil into wires, and it's quite ingenious. So I have a feeling that aluminum is also going to be a fairly good conductor. And brass is a mixture of copper as well as some other metal, but it's a lot of it's copper and zinc mixed together is brass. So copper plus zinc is equal to brass. And as we know, copper is a good conductor, so since copper is a primary ingredient in brass, we can pretty much say that brass is gonna be probably a good conductor. Okay, but how we actually measure this is with resistivity. Resistivity is kind of like density. Yeah. So it's we want to pretty much see, like, we can get the resistivity values from each of the metals. The units is ohm meters. So if you have like resistivity divided by the length of like a wire, we're going to assume a wire, it would have like resistivity divided by length is equal to like ohm meters divided by meters, and that would just be, the meters would cancel out and that would just be ohms. So you would just divide it by the distance that the material is like a wire for. But there are kind of different ways of measuring resistivity depending on like the thickness and stuff, but we don't really need to get into that. We pretty much just say whoever has the most ohm meters, the most resistivity, that is going to be who is the worst at conducting, because higher conductiveness means you have lower resistance, and resistance is measured in ohms. And there was a scientist named Ohm that was like the founder of all this, and so we pretty much want the least amount of ohms possible, and copper is very low as predicted, as well as aluminum and brass. And surprisingly, nichrome is a quite good insulate, or I wouldn't say quite good as an insulator. It's the least conductive because it has the highest resistivity. Another relationship that can help keep this in your mind is resistance is equal to the inverse of conductance. Okay, so if you want to know like how resistance and conductance are related, they're just inversely equal to each other. Okay, so nichrome is going to be the worst at being a conductor because its resistance is the highest. Okay, and yeah, and that's fascinating. So is there any utility to being a poor conductor? If you have a lot of resistance, that means that you are kind of as electrons fly through you, more resistance means that those electrons flying through you are losing some of their velocity. Okay, and as they lose their velocity, that velocity that they're like bumping into all of those atoms in the wire, and when they bump into there for a highly resistive thing like nichrome, they are transferring their potential energy into the potential or their kinetic energy into the kinetic energy of the material itself. And we all know that the average kinetic energy of the particles inside something define its temperature. So, a very hot plate, for example, there are a lot of very quickly bouncing around particles that make up that hot plate. But as it cools down, those particles inside are going to slow it down. So things with high resistances often are good for use as heating elements, which is kind of what the junior tutor has written here, and that's an awesome answer. So the above solution is not only good, the above solution is great. Solution is excellent. Great to see it. Yeah. Excellent. Solution is good. Awesome. Let's ain't this a lot of fun? Whole lot of fun. Okay, we can keep it moving to the next question that we got on the menu today, which is, what is spring potential energy? Well, spring potential energy is the potential energy that is held inside of a spring. Actually, perfect. I have a very good example of a spring potential energy right here. So this is just like a grip trainer. It helps you get stronger hands. I'm trying to get my deadlift strength up, so it's important to have a good grip. And you see there's a nice big spring here. When I have this compressed like this, like I got to put in some work to I have to be constantly applying a force to stretch out the spring. But as the spring is stretched out, it has potential energy inside. Why? Because at a moment's notice, I could, kind of like this. It's kind of dangerous to do because this is a strong spring. I could just let it go, and I could allow this spring to contract itself, because when it's stretched out, its potential energy is saying, like, I have this much energy of me wanting to return to my original state. This spring does not appreciate being stretched out. It is applying like a force to kind of revert to its original thing, and that force is why this stuff would be useful for training your grip if you're trying to get your deadlift, if you're trying to lift heavier stuff. Okay, so that's what spring potential energy is. Another example of spring potential energy would be you ever see like a slingshot? So a slingshot, when it's unstretched out, there's no potential energy. But when you stretch it out, you're quite dangerous in here, because at a moment's notice, you could let it go, have all that potential energy inside the slingshot be transformed into kinetic energy in the projectile, sending it flying, hopefully to a non-living safe target. Okay, so those are just some real-world examples of where you might see spring potential energy. So real cool stuff. Now, how would we calculate that? Well, we know that the spring force is given with Hooke's law. Hooke was a pretty smart guy who probably studied strings a lot. Yeah, Hooke's law. Hooke's law states that the force of spring is equal to spring constant multiplied by the displacement of the spring, or the amount of stretch or compression. Stretch or compression of spring. Okay, so with my little grip trainer here, just a little bit of stretch, like that would be a small x value. I'll actually write it out in letter form. Equals k x. With a little bit like this, that's a little bit of x. But when I really stretch it out more, even if it's just by like a couple millimeters, that increases x a lot, increases the amount of force. So it's a lot harder to hold it in this position as opposed to in a more loose position. That takes less force to maintain as opposed to really tight, Ooh, my hand's gonna be pretty strong after this. And the K is like the strength of the spring. So, this spring right here is going to be a lot stronger, or that's going to have a much higher K value than in maybe a mechanical pencil. There's a spring in there that's going to have a small K value because that spring has less force that's going to be applied. Okay, so yeah, that's pretty cool. And we also know that work is wait a minute. I'm not sure work necessarily relates to this. Yeah, so here we have like a graph. Yeah, I don't think necessarily work relates to this, but the equation. See this graph here? It shows us that the more that we deform the spring, or more we stretch it out, more we compress it, the more that we're going to interpret a force. And it's a linear relationship, and with the coefficient of k. Now this is only true within the elastic limit of the spring, but we don't need to worry about the elastic limit. We're going to assume that we are having a hooky law. Yeah, we're not playing hooky here though. Anyways, yeah, so the work that, okay, I guess work is related. When we apply a force to the spring, the amount of potential energy that is absorbed is going to be proportional to the amount of work that we put into the spring. And that is the area, the work is the area underneath the force displacement curve. Now you see how it's a triangle? Because it is a linear relationship, that means that we are going to have a, well, the area of a triangle is equal to base multiplied by height divide 2. Okay, and the height is going to be the force. Let's rewrite this. So we know the potential energy. Let's call that U. U is often used for potential energy. I think it's because like it kind of sounds like there could be a U. And P, the letter P, is used for momentum. Now, why do we use P for a word that doesn't have the letter P in it? No idea. It's just the way that it is, and everyone's kind of scared to change it now and then have every previous textbook be invalid. So we keep it moving with these imperfect calculation or imperfect symbols, even though they don't necessarily make sense all the time. But yeah, so our base in this case is I guess the deformation. So let's just be D. Another way that we can write D is X. Yeah. And then our height is our force, but we know from our force it's just kx. And then divide by 2. And we can rewrite this as 1/2 kx squared. That's the potential energy that you put inside of a, or that's the potential energy inside a spring once it's compressed. Of course, if there's no compression, if x is equal to 0, no compression, no potential energy. A lot of x, a lot of potential energy. So this will be potential energy of spring. Of spring. Now, something interesting that I want to note is kinetic energy is equal to 1/2 mass times velocity squared. You kind of see how they have, I'll write it kinetic energy so it's not confusing. You kind of see how they have the same type of structure. They have 1/2 times a constant value, the spring constant for spring potential energy, mass for kinetic energy. Those are constant. You're not going to change your mass that much, hopefully, or in most cases. And then you have multiplied by some property squared, the compression squared for springs, and the velocity squared for kinetic energy. It's quite beautiful how there's a lot of similarities in a lot of things that we see in physics, because everything in the universe is related through physics, and there's a lot of parallel things that are going on when that are really, really beautiful to me. So I feel like just how this is the equation of potential spring energy, or potential energy inside a spring. Sometimes people use D instead of X. That is perfectly valid as long as you recognize that it represents the value of how much that spring is compressed or not. And yeah, it's really a beautiful thing. Beautiful thing. So The above solution is good. Is good. Cool. So, the next question that we got on the menu today, oh, I really like this question. It's about electric flux. So the question is asking us, find the net electric flux through the cube shown on, I guess, this image. Can we use Gauss's law to find the electric field on the surface of the cube? Okay, so the first part of the question is asking us, how do we find the electric flux through the cube? And inside there we have a 3 nanocoulomb charge. We don't know what that particle is. It honestly doesn't even matter. We just know that we have a cube and we have this outside here. Now let me tell you what electric flux is. Electric flux is a property that's it's pretty much given a hypothetical surface. Surface. How many electric field lines pierce the surface? Now this was the definition that my first year physics professor gave me. Is like this. Now, something that goes in, like an electric field line that both enters and exits, does not contribute to the flux. So an E field line that enters and exits surface. Surface does not count. Example, if this was the surface and this was an E field line, not count. And the reason why, it enters the surface, but it also exits the surface. So yeah, that's why it doesn't count. So really what only matters, only the charges inside matter. Charges inside the surface matter. Okay, so yeah, the equation that we can use to get the electric flux is as follows, given the enclosed charge. Now, the reason why only enclosed charges matter is, like, let's say we have a charge, let's call it Q. Q is typically used for charge. And let's say our surface is green. It doesn't matter if it's like a cube, a circle, or like a potato chip bag. Like, it can be any shape you want. The flux is always going to be the same as long as the internal charge is the same. So the surface actually doesn't matter at all. Yeah. Now you could do this with the surface integral. That is really hard and not necessarily, or not at all, the easiest way to do this. Now if we have like electric field lines here, like you could see how that's only exiting. So they count. Let's call that E fields count because only exiting surface. And even if we have a situation like this, like we have a Q inside a surface that is like this, and we have an electric field line, well, it exits, enters, exits, enters, exits, enters, exits. You will see that even though it's entering and exiting a lot, these two neutralize each other, these two neutralize each other, these two neutralize each other, but then there is one here, so only one exit. Only one net exit. Okay, so even if you have a surface that kind of looks like a comb, and your electric field line is going to pierce through the surface multiple times, the exits and the enters, they neutralize each other. So regardless, it's always going to be what's inside, even if it looks like the electric field lines are piercing through the surface multiple times. The net effect is that if the charge is inside the surface, it is impossible for any of the electric field lines to cancel themselves out. So there's no way that you can leave the surface and come back in and have the charge still be inside. But then again, the charge is outside of the surface, they will never contribute to the flux inside. Okay, so now let's put some equations to this. The electric flux is represented with the Greek letter, I'm pretty sure that's chi, but I just remembered as capital I with a circle in the middle. So that's the symbol for electric flux. Symbol for efflux. And this is equal to the charge that's contained inside divided by a constant called epsilon naught. And epsilon naught is a constant that is also known as permittivity of free space. Now, generally, we're going to use the permittivity of free space, but this is really dependent on the material that you're currently, analyzing. So if you're doing this inside of water, you're gonna have a different epsilon value. It's gonna be like the permittivity of water. Or if you're doing this inside glass, it would be like the permittivity of glass. But in general, like when we're on the atomic scale of individual charges, we're typically going to have the permittivity of free space, because if you really, really zoom into things, there's nothing there. Everything is pretty much made of nothing. That's a wild thing to think about, but it's a beautiful property of our universe. Okay, so the epsilon naught value, it's epsilon, not E. That was not a very good drawing of it. Let's rewrite that. The value that it has is, asking Google, is 8.85. We don't really worry about all that decimaliciousness. 8.85 times 10 to the power of negative 12 multiplied by seconds to the power of 4 times amperes squared over meters cubed kilograms. Yeah, that is a scary unit, but it's nothing to be worried about. So if we go back to our question, we see that our Q value here, so this is a constant. Our Q value, let's use purple. I think purple, I just get the feeling that charge is like a purple quantity. I don't know if I got synesthesia or not, though. I just feel it feels purple. So our charge is positive 3.00 times 10 to the negative 9, because 10 to the negative 9 is just another way of saying nano. 10 to the negative 9 coulombs. Okay, so if we want to calculate the electric flux, well, we just do that division real fast. Times 10 to the negative 9 coulombs. All divided by 8.85 times 10 to the negative 12 seconds cubed amperes squared per meters cubed kilograms. I didn't say seconds cubed, I said seconds to the 4. Okay. So the unit of this whole thing or the magnitude of this result, 3 times 10 to the power of -9. Divide that whole thing by 8.85 times 10 to the power of -12. Oh, that looks like a -2. That's -12. And the result of that math is 338. Did the junior tutor come to the same conclusion? No. Oh, they use 3 instead of 3 to the power of -9. So, can't forget that that nano there. So the actual result is going to be 3.39. Actually, it's just going to be 339. 339. This is rounding to 3 sig figs because that's how many significant figures we were given in the question. Of course, it's a quite long and decimalicious answer, but we only need 3 significant figures, so we can. And this is our final answer, so we're good to round here. And then our units, we have coulombs on top. Then the downstairs here, those go on top as well. So those are going to be meter cubed kilogram per seconds to the power of 4 amperes squared. Amperes is also known as ampere is equal to a coulomb per second. So we can also rewrite this unit as coulomb meter cubed kilogram seconds 4 multiplied by coulomb squared per second squared. Second squared, this becomes squared. So 339. The coulomb squared, neutralize the coulomb up there, so it's going to be meters cubed kilogram per second squared coulomb. Okay, so that'll be the unit for electric flux. Yeah. And this was all calculated with Gauss's law. Now, Gauss's law, if we know the flux, just by knowing the charges inside, let's actually search up the equation for Gauss's law. Is equal to this. So if we wanted to find, this is where it comes from for Gauss's law. Gauss law is that the flux is equal to the surface integral of the electric field with respect to the differentially small area is equal to the Q over epsilon naught. And now to find the electric field, we would need to know about the surface, and this really gets deeper into the surface integrals of cubes as well as other surfaces, because typically when you do surface integrals, you don't always get nice easy shapes like cubes, but using this equation you could solve for the electric field at a certain point, but you need to know stuff about the surface, and since it's just a cube and we don't really know, or we know what the flux is, but we don't really know like that many properties about the cube, it's going to be a little bit more difficult to handle this. So I might hold off on that on now, because I do have some other questions left to do on this session. So the above solution is good. Actually, the above solution forgets the times 10 to the power of -9 factor on the charge when calculating electric flux. Also does not comment on using Gauss law to find the electric field given the electric flux. Okay, the next question that we got on the menu today is a potter's wheel. I guess that's like, you ever seen people, turn clay into pots? They have those wheels and they spin it with their feet and then they mold the pot. That's what a potter's wheel is. Rotates with an angular acceleration of alpha equals 4at squared plus minus 3bt to the power of 3. Okay, so let's write that out, but let's write it out like this. So we have our angular acceleration. And we got alpha as our angular acceleration. And let's write our high degree term first. So it's going to be negative 3b t cubed, negative 3b t to the power of 3 plus 4at squared. And the reason why I want to order the t terms like this is because we're going to need to take some, we're going to need to do some integration for the rest of the question. Actually, I'm kind of getting my head on myself. Okay, so let's actually get through the rest of the question. So we're given the angular acceleration with this equation, and we have t, which is time in seconds. A and b are constants, so I mean we can just leave them as is. We don't really need to worry about them that much. They're just constants. And alpha has units of radians per second squared. So let's write that out. Rad per second squared. The initial position of the wheel is theta naught. Initial position is theta naught, and initial angular velocity is omega naught. That's not a W, omega. Initial velocity, angular velocity, is equal to omega naught. Okay, and now we need to find equations for the angular acceleration as well as the angular position. We need expressions for angular velocity and angular position. I think it means angular position instead of angular acceleration because, I mean, it's right there, of the wheel as a function of time. Okay, so let's think about how velocity, position, and acceleration are related. So we know that we have theta. This is our position. D over dt of theta is equal to our omega, which is our velocity. And then we have d over dt of d over dt theta, which is equal to d over dt. The derivative of omega is equal to the angular acceleration. Okay, now if we're trying to go the other direction, omega is equal to the integral of acceleration with respect to time, and the position likewise is a similar type of thing, which is the derivative of velocity with respect to time. Okay, so these are equations that we're going to use, and then let's sub in our known equation for alpha, angular velocity, to help us determine this. Okay, so it's pretty much just a integration problem that we have to do. Two integration problems because we need to integrate it twice. So we have omega is equal to the derivative of negative 3bt cubed plus 4at squared dt, and this will be our omega term. Okay, time is kind of tight, so we do need to I'll need to speed this up a little bit. Okay, no issue. Now to do the integration, this is fairly straightforward. We increase the power by 1 and then divide the whole thing by the same number as the new power. So this is going to be omega is equal to 1/4 multiplied by negative 3b t to the power of 4. And then we're going to do something similar for the next term. So this is going to be 1/3, because 3 is going to be the new power. Multiply that by 4 at3. And don't forget this, plus c, constant of integration. Okay? Yeah, so this is what our equation looks like now. We could rewrite this as omega equals negative 3 over 4b, negative 3b over 4t to the power of 4 plus 4 over 3, no, 4a over 3t cubed plus c. And we know that the initial angular velocity is omega 0. So we know that at t equals 0, we're going to have omega naught is equal to, is just going to be equal to negative 3b over 4t to the power of 4, but that's going to be 0. Same thing for the next term, 4a over 3t cubed. That's going to be 0 with t equal to 0, plus c. Whoops. So given that, c is equal to omega naught. Okay, so that's awesome. So our omega term is equal to negative 3b over 4t to the power of 4 plus 4a over 3t cubed plus omega naught. And that would be one of our final answers. And is that what we see on our... this integration is not done properly. That's alarming, but we'll get through the right answer. So this is our first omega term. Yeah, okay, that's no worries. We'll just need to report that. And then if we want to take the this is our omega term with respect to t. Maybe it'd be better to say omega with omega t. But we know that our theta, our angular position, is equal to the integration of omega t with respect to t, which is just the integration of negative 3b over 4t4, put this whole thing in brackets, plus 4a over 3t to the power of 3 plus omega omega naught, actually. I know my British friends really like saying omega naught instead. And this is respect to dt. Let's do the integration super duper fast because time is kind of tight over here. So we're going to increase the power by 1, and we are going to put the power in the denominator of that function. So it will be negative 3b over 20 t5 plus 4a over 12 not t2, t4 plus omega o t plus c. Now, if we set t to be 0, we know that when t is equal to 0, initially the position is going to be omega naught. And with the same thing before, when we set t to 0, all these first three terms become 0 themselves, and c is going to be equal to theta naught. So we know that c is equal to theta naught. Given t equal to 0. And that would be our final equation here, is theta equals to negative 3b over 20 t to the power of 5 plus the 4 and the 12, they'll neutralize each other, so it will just be a over 3. Yeah, a over 3 t to the power of 4 plus omega o t plus theta naught. And that would be our final equation for the position, the angular position. And we showed this through the process of integration. Okay, the only issue here that I see is that the answer does not agree, or the equation used in the answer does not agree with the equation given by the question. The above solution is incorrect. The angular acceleration equation for the given is different from the one used in the solution. Using the equation. Okay, cool. Now, unfortunately, we are kind of running out of time, which is sad because I would love to keep going, but I do have a schedule that I do need to respect. So let me just switch my screen real ASAP fast. Yeah, so those are all the questions that we have time for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring the notification bell below. If you would like to submit your own question, there are links in the description of this video below that can help you make an account with OneClass to help you ask your own questions. If you enjoyed the video, please leave a like and leave a comment talking about what you think about the video. If you really enjoyed this video, feel free to share it with your friends. This has been Millan with OneClass, and I hope to see you again soon. And don't forget, physics is always a fun time. Take care, have a great day or a great evening, or, just have a great time. Just have a great time in life. How could you not have a great time with physics? That's what I'm feeling. Anyways, take care. It's been a great stream. Hope you have a great day.